Hello friends, welcome to the 24th module of AI. In this particular module, we will be discussing about knowledge representation. We will begin our journey of representing knowledge now. We will begin with the simplest method called propositional logic in this particular module. We will be also extending our discussion to something called predicate logic in this particular module. Both of them are quite useful in representing knowledge and inferring from it. These two are the most important requirement of any knowledge representation scheme that anybody would discuss. We will be discussing a few schemes which are normally used in knowledge representation in few modules from now. Predicate logic is the basis of that, and propositional logic actually forms the platform on which we can discuss our predicate logic. And the propositional and predicate logic together are known as formal logic. What does that mean? The logic is something that all of us use, but the formal logic is something which can be written, which can be programmed, which can be used for systematic providing a systematic proof for anything that we would like to talk about. When we talk about knowledge representation, please understand that whenever we discuss about any problem, for example, missionary cannibal problem that we have discussed, a traveling salesman and whatever, even you talk about Block's world problem, whatever problem that you talk about, you need to store that information somewhere and you need to infer from that information. We will be discussing about that precisely in this particular module. We will begin with our discussion on something called formal logic. I have already told you that this formal logic is something which is a systematic way of representing something in form of a logic and inferring from it. This inference is again a very important point. We will be talking about that soon. And two things which we are going to discuss in this particular module are propositional logic and predicate logic. We will soon see the difference between these two as well. One of the most important thing about representation of knowledge is that we will have to have some structured form in which we can represent. Why structured? Because we need to infer from it. Not only we need to infer, we might need to share that information with something else. And a lot of other knowledge representation schemes are seen in this world today. One of the most common and most powerful one way is using XML, and AI and XML are meeting at some place also. We have discussed about agents, and when agent has to take decision, what he has to do is to look at the knowledge base that it has, the information, the statements or whatever represent the current state of the art and whatever the other information that it has. It has to look at that and decide what to do next, and that is called inference. That is what precisely is the need of the hour, and that is what we are going to address here. Okay. And we have seen the state space case, we need to define the problem state, and we also have to define the rules, and we did something in the initial modules without really telling how exactly one can form this thing. Okay. And now we are going to discuss a formal method of representing statements and rules here. The basis of this particular logic, formal logic, is something called symbolic representation. Whenever we would like to define a problem, like on A B and on table B and something like that we have seen, and earlier when we have discussed missionary cannibal, we had M1 C1 M2 C2, those things are called symbols, and the structure that we construct out of it is called symbol structure. So, basically what we are discussing is that you need some kind of symbol structure, some way to represent symbols, some way using symbols to make sure that we can infer from it, we can conclude something from it, we can prove something from it. Newell and Simon, two scientists long back, years before, provided something called physical symbol system hypothesis. The hypothesis says that if you have this physical symbol system is something which is collection of symbolic structures, like something that we have already seen earlier, like missionary cannibal problem and the farmer fox chicken grain problem, and all those problems we discussed. We actually have, we have not named it so in that particular module, but it is basically a symbol structure. So, such symbol structure is called physical symbol system. It is capable of intelligent action. That is what they said, and we have already done that, and we could find solutions to farmer fox chicken grain and all those problems using those symbol structures. So, that is what they said, and the most important outcome of that particular physical symbol system hypothesis is that it is possible to have some intelligent action if you have some symbol structure, and this is what we are going to do here. Okay. Real world problem, when you want to solve, sometimes you need non-real world entities also. For example, if I want to find out and work on sofas and chairs and something like that, to make sure, for example, is a program which helps an architect person to, or somebody who is decorating home, to make sure that the room looks pretty nice with all amenities. So, it adjusts sofas and chairs and all that across room to make sure that it looks great, or it provides options to the user. So, user can choose one of the structures. So, when it has to do that, if you have to do it programmatically, if you have studied C++ and Java, you probably understand what I am trying to do. You have to have an abstract entity called furniture. The furniture is not actually a real thing. Chair is a real thing, sofa is a real thing, but furniture is not, it is an abstract concept. But when you do programming, you need such abstract concepts. So, that is again an important thing. There are two types of entities. One is a real world entity, and this is something which is non real world entity, something which is required to be added for programmers convenience. So, both of them are needed. So, whenever you talk about symbol structure, the symbol structures comprises of both real world as well as non real world entities and some relations between them. So, when we begin talking about logic, we begin with the first thing called premise. The premise is something which is known to be true. For example, when I say that Ramji is man, or Sachin is cricketer, okay, or Jagdish Singh is a singer. Now, these are the statements which are known to be true. So, they are known as premises. So, anything, whenever you talk about logic, you actually, the logic is resting on something which is known to be true at any given point of time, and they are premises. Okay. And the second point, as I said, you need two things. One is storage, the other one is inference. How do you infer? And there are many ways of inferring, and I am not going to discuss about the ways of inferring. We are not discussing logic, please understand. We are only discussing predicate logic and propositional logic, some form of them. But anyway, let me talk about one typical way to infer is called syllogism, which is something which is most commonly used. When you say A implies B and B implies C, that means A implies C. For example, Sachin is a cricketer and a cricketer is a sports person, then Sachin is a sports person, kind of inference, that is called syllogism. There is an example given on the slide. Vijay is a teacher and all teachers are educated, that means Vijay is educated. Okay. The other one is Radha is a housewife and all housewives like to cook, that means Radha likes to cook. Okay. So, these are examples of syllogism. When x implies y and y implies z, that x implies z. But please understand that in not all cases this can be done. For example, one very interesting example is Sachin is a sports person. Sports persons are found all over the world. That means Sachin is found all over the world. Now, that is not correct. So, not always this is the case. You may be surprised why the third one is wrong. Okay, let me tell you why it is wrong. Because when you talk about an attribute, the attribute are of two different types. One belongs to the class itself. The other one belongs to the elements of the class. Whenever the attribute belongs to the element, it can be used for further implication. The attributes which belong to class do not. For example, sports person, the attribute spread across the world is not something which is an attribute of the element. The elements won't inherit that particular attribute. If you know bit of programming, such things are stored in form of static variables in object oriented programming languages. So, this is something which is very interesting. But anyway, syllogism is one way of inferring. There are a few other ways of doing that. But anyway, what we want is, we want to store information, we would like to infer from it. And whenever we infer, what will happen? Suppose if I have in the beginning I have 5 statements and now I infer the 6th, 7th, 8th. The next question may come to your mind is, if I have this set of 5 questions, how many more set of 5 statements, how many more statements can I generate which are again true, which are inferred from it? Whatever you can generate is called entailment, and it depends on two things: the amount of knowledge that you have and the methods of inference. You use more and more methods of inference, you will get larger and larger data set. And not only that, though the additional statements that are added, again they are part of the database and again you can infer further from them. Okay. So, that entailment is again, it's quite interesting part. Again, we will not be discussing this thing further. What we want, again, please understand, we are interested in writing an AI program which can learn, store information and go further from it. Okay. You may ask a question, how do we get the premises, the something which is known to be true? It's pretty simple. You have all 5 senses. People talk about 6th sense, but we will not be discussing while we are discussing AI. So, you have 5 senses and you get lot of information from it. You know somebody is man, so you say that Ramji is man, or Sachin is a cricketer. You know Sachin is a cricketer because you've seen, you've read, you've listened. So you get that information. So you write down Sachin is a cricketer, and so on. So that information is coming from all 5 senses. Please understand, the inference is coming from within. See, the premises are coming from outside. That information is coming from outside. Logic which runs inside the brain generates additional statements. Okay, they infer from it. So these are 2 different processes. If you look at something called Felder-Silverman model, which I mentioned in the write-up, they talk about 2 different type of learners called sensors and intuitors. Sensors are people who get information from outside, and the intuitor is somebody who generates that from within. In fact, everybody is both sensor and intuitor. So here is a classic way of describing how this thing is happening. The premises are something which are coming from outside, and the rest, the inference, is coming from within. Okay, now we will look at some of the common symbols that are used in both propositional as well as predicate logic. The screen talks about them. One is implication arrow. A implies Y, means when A is true, B is true. And A and B means A and B, both of them are true. A or B means A is true or B is true. Not A is whatever the truthfulness of A is negated. So, if A is true, not A is false. If A is false, not A is true, and so on and so forth. And there are 2 more qualifiers which are used only in predicate logic, they are not used in propositional logic. Okay. One is used for all, and the other one is used for their exist. Okay. They are known as universal quantifier and existential quantifier. These 2 are very important ones used for most predicate logic problems that we talk about. Okay, here are some statements on the screen that you can see. There are 5 different statements. The first one is Sachin is a cricketer, Saina is a badminton player, Sania is a tennis player, Jay is a badminton player or a tennis player. If Sachin is a cricketer, he is a sports person. Now, if you want to represent these statements using propositional logic, here is what it is. The first one, Sachin cricketer, is a single phrase which describes Sachin being a cricketer. Saina badminton, Sania tennis, Jay badminton or Jay tennis. Sachin cricketer implies Sachin sports person. You can see this is a pretty simple way of representing the knowledge. In many cases, people do not use this long phrases, they use only single character representation, like Sachin cricketer you just have P, and Saina badminton will have Q, and so on and so forth. What is the advantage? The advantage is that you can represent statements, a huge long statement in a very short form. The next slide shows you that P is Jai is a cricketer, Q Jai is badminton player, R is Jai sportsman, and S Jai lives in Ahmedabad. And if you want to state something like that Jai lives in Ahmedabad and he is either a cricket or a badminton player, we can represent that as and in the bracket P or Q. Now, you can see that is a very compact way of representing, obviously not very readable, but then it is good. Both forms are used. Instead of P, you can write a phrase which is more readable than P or Q, but if you use P or Q, is very compact. So, both ways you will have to look at the requirement and decide the form that you probably would use. Okay. With propositional logic, there are a few ways of inferring, but here 2 very known ways of inferring are shown. For example, you have P and Q. Both of them P and Q, and then P or Q. Suppose you know P is true. Obviously, the P or Q is true because P is true, you know that. Okay. Not only that, if you have P and Q and you know P implies Q, and again you know P is true, you can conclude that Q is true. Now, these are 2 simplest ways of inferring in propositional logic, but then this is a problem. With propositional logic is a very elementary form of representing knowledge, and that is a problem. The problem is that how you relate to relations. For example, if you say that Sachin is a cricketer and cricketers are very rich, you like to prove Sachin is rich. How do you do that? It is impossible using propositional logic, but you can look at the example shown on the screen. It is example 24.1 in the write up, which shows, okay, you can see that the same information that we had plus the information that all cricketers are rich are shown in this thing. You can see that cricketer Sachin, badminton Saina, tennis Sania, badminton Jai or tennis Jai, and then you can say for all X, cricketer X implies rich X. Now, this is very simple but very elegant way of telling that if X is a cricketer, then he is rich. And what you will have to do, you will have to just say that X equal to Sachin, then you can prove rich Sachin. Okay, so, that is how. Another example that comes next is there on the screen. Okay, Mama Bajrangi Shahida, brother Shan Sagarika, father Rajiv Rahul, and relation Gujarat capital Gandhinagar, Gujarat large city Ahmedabad. These are examples of predicates. A predicate begins with a name, okay, that in mama, brother, father, relation, these are names of predicate, and the information enclosed are the arguments. Like Bajrangi, Shahida, Shan, Sagarika, they are called arguments. Okay. For example, for father, there are 2 arguments, Rajiv and Rahul. For relation, there are 3 arguments. In fact, I have also tried to show what is second order logic. If you have one more enclosure, it becomes second order logic. Okay. The last 2, relation, you can see that relation Gujarat, and under Gujarat, you have capital and Gandhinagar and so on. So, it is called second order predicate logic. We will confine our discussion to first order predicate logic for this particular module. The discussion that we have can easily be extended to second order predicate logic. Basically, our information, what we are going to talk about is representing information and inferring from it. If you infer in more complicated form, second order predicate logic, finer inferences can be drawn, but anyway, that is what we are talking about right now. Okay. So, the structure of predicate, you have seen that it begins with a name and you have arguments. Number of arguments in a predicate is called arity of a predicate. Okay. Some predicates have arity 2, some predicates have arity 3 and so on and so forth. Usually, for our discussion, we will have predicates with arity 2 only. The order is very important. Please understand, and order depends on us, the person who is going to code. For example, one very interesting example that I have quoted in write up is Mama Kans Krishna and Mama Krishna Kans. These 2 are different. Okay, because if you say that the first one is a nephew and the second one is mama, obviously if you change the order, the problem could be that if you write Mama Shakuni Duryodhan and actually you should have written Mama Duryodhan Shakuni, what happens is when you say Mama Duryodhan Shakuni, Duryodhan becomes Mama of Shakuni. What does that mean? He is also mama of his own mother, and if somewhere you have information like son Duryodhan Gandhari and you also prove that Duryodhan is Gandhari's mama, what will you get out of it is Duryodhan is his own grandpa. Okay. Now, it's very simple example. What I am trying to quote, I am trying to convey is that it is very important for you to make sure the order is maintained in the representation, and there is no strict guideline. In fact, it is all designer's choice. You design the predicate, you decide the order, and if you fail to design the right order, you fail to maintain that right order, probably you will conclude something which is absolutely wrong. Okay, so that might happen. This is the example. This is a very simple example which you can see the implication of forgetting the right order can be quite disastrous. You will prove something which is absolutely wrong. And please understand, the predicate itself has nothing to do with truth or false. For example, if I say man X or cricketer X, it is neither true or false. If I say that cricketer Sachin, it is true. Cricketer Jagdish Singh, it is false. So, cricketer has nothing to do with truthfulness or falsehoodness. Okay. It is the argument which decides the truthfulness of that particular predicate. So, in fact, the example that I have shown on the screen is player Anand, not player Jagdish Singh, not singer Anand and the singer Jagdish Singh. All 4 can be true at the same point of time. So, some singer is true, some singer is false, some player is true, some player is false at the same point of time. What does that mean? Again, is that predicate has nothing to do with truthfulness of anything. Okay. Whenever you provide an argument to the predicate, it decides the truthfulness or all the falsehood of the statement. Similarly, when you have the variable, okay, for example, player X, unless X is bound, you cannot determine the truthfulness of that particular statement. Existential and the universal quantifier are very important. Universal quantifier means that the statement is true for everybody in given domain. For example, when you say that for all X, player X implies reach X, every player, whoever you qualify as player, for him being rich is true. So, that is, or for all X, housewife X likes to cook X, means that everybody who is a housewife, this statement likes to cook is true. And existential quantifier is different. When you say that a player X, there exists X, player X implies singer X, that means that there are some players who like to sing, they are singers, not all. Okay. So, existential quantifier is the statement is true for a subset of the values, okay, and for universal quantifier the statement is true for all the statements, all the members of that particular domain. Okay. Here is an example again given on the screen you would like to refer to. The first one is all the players are physically fit. So, you say for all X, player X implies physically fit X. Okay. Some of the players are singers, you say that for all X, there exists X, player X implies singer X. Now, you can see that the for all X and there exists X. Okay, the difference. The example 24.3 is, it talks about how you infer from something which is given. if you read 24.3, you realize that like it is Anand is a player, Anand plays chess, Anand was a world champion, Anand has beaten Gary. If somebody has won the match, he has played that match with the opponent. If you read that, you can easily confirm that Anand has played a match with Gary. Now, how do you prove? When you want to prove this, you will have to convert this thing into predicate logic, and then you will have to have some method of inference. So, this is what we will do. Okay, you can see that predicate logic representation on the next slide. Player Anand plays Anand chess. Now, you can see that representation omits some important things. For example, Anand is a player. So, that the present tense is missing from this representation. If I say Radhakrishnan was a player, I will only have the representation as player Radhakrishnan. I have no difference between player Anand and player Radhakrishnan. The Anand being player now and Radhakrishnan being player in past does not make any difference in the representation. So, while we represent, we are going to miss something, but usually we will retain something which we need to use and will omit things which we do not. And the other one, world champion Anand chess, you can see that can be represented in little more better way, but this is a very crude way of, but very simple way of representation. Okay, beat Anand Gary. And the last one, for all x, for all y, win x y means played match x y. Okay, again played match, you can see that it is a single short predicate and a simplified predicate. And here is how you prove. For proving in predicate logic, what you do is you just pick up that statement which you want to prove, convert that thing to predicate logic, and then use that thing, find out if there is an RHS somewhere right hand side. So, for x implies y, and if you want to prove y, obviously you will have to prove x. If x is proven, y is proven. So, what you do is you find this y in the right hand side of some particular rule. So, this is what precisely we have done. Okay. So, what we want to do is to check played match Anand Gary, but for which you need to make sure that Anand has won, but that is not there. We have a statement which says that Anand has beaten Gary. We do not have a statement which says that Anand has won against Gary, but that is obvious. When somebody has beaten somebody, he obviously has won. So, that statement is missing from the representation, the earlier one. We will have to add. So, that is the sixth statement which we are reading, and now you can see that how it proceeds. So, played match Anand Gary, which can be proved if we prove win Anand Gary, which can be proved if we prove beaten Anand Gary, which is there in the statement. So, it is already proven. So, we have proven what we want to. Okay, what is the difference between this universal and existential quantifier and how to use them? One example is shown on the screen. For example, you say that when every student like all AI modules, you say that for all x, for all y, student x likes and module y likes x y. Now, the same statement, if you use existential quantifier, makes it very different. It says every student like a module. For all x, there exists y, student x and module y likes x y. Now, the statement is same, the quantifier is different. Here, not every student liked all modules. Some student like some other student like some other. It is different for different students. Okay, so you can see that there is an existential quantifier for y. Case number 3, every student like module number 13 or module number 5 or whatever. So, in this case, the last one, for all x, now that there is no quantifier here, you can see that there is no quantifier needed. It says that for all x, student x and module AI2. Now, AI2 is a constant value. Okay, and like x AI2. Okay, so you can see that y in case number 1 was universally quantified because it is true for all of the modules. In case number 2, it is existentially quantified because it is true for some of the modules and not for all. And the last one, it is not quantified at all because it is true for only one constant value which you can directly represent. You do not need a variable. So, these are 3 important statements which clearly indicate the difference between these 2 quantifiers and a constant value. With that, we will come to the end of this particular module. What we have seen in this particular module, we have talked about knowledge representation schemes. We begin with the simplest knowledge representation scheme called using propositional and predicate logic. Propositional logic is something which uses a single symbol to represent a statement. A predicate logic is a little more detailed. It begins with a predicate name and then there are some arguments. The arguments which define the truthfulness or falsehoodness of that particular predicate. And whenever we do that, what we are doing is we are representing anything given the statement in form of some symbol structure. According to Newell and Simon, such structure is capable of intelligent action. We have already seen that while we were discussing problems in initial modules like missionary cannibal problem and traveling salesman problem and so on and so forth. We are going to do that in subsequent modules as well in little more structured and formal way. And when we represent logic in either using either propositional logic or predicate logic is basically known as a formal logic. Okay. So, and there are two important things when we talk about logic. First is representation, how you represent statement or any given information. And we have seen when we have looked at one very simple example that when we wanted to prove that Anand has played match with Gary, many a times even the simplest case we miss some obvious thing, like for example, bitten x y means somebody x has won against y. So, that is very obvious simple information which was missing in the representation. So, one of the very major challenges in representing knowledge is this thing, which we will explore further in the next module. Okay. So, these are, and we have talked about propositional logic and predicate logic, and we will be talking about that further in the next module. With that, we will end this module. Thank you.